In the previous two lectures on harmonic oscillator, we looked at a free harmonic oscillator for which the equation of motion was k x equals 0. Then we looked at a damped harmonic oscillator where there was some damping proportional to the velocity, and the equation of motion was like this. We defined the quality factor, looked at this damped oscillator in the region of heavy damping, critical damping, and light damping. In today's lecture, we are going to look at another aspect of an oscillator, and we are going to ask what happens if I apply a force on the oscillator in addition to it being subjected to a force by the spring and its mass being m. The simplest case is that of a constant force on an oscillator, and you already know the answer. In this case, all that happens is that the equilibrium point gets shifted. You know the answer of this, I said, because you already know the example where if I take a spring, put a mass on it and put it vertically in the gravitational field. In that case, this is being pulled by a constant force mg, but still the equilibrium point shifts and still oscillates about the equilibrium point. To see it mathematically, let us write the equations of motion. Mx double dot in this case is going to be equal to minus kx plus whatever that constant force that I have applied, and therefore, mx double dot plus kx is equal to f. Dividing by m, I can write this as x double dot plus omega 0 square x equals f over m, where omega 0 is square root of k over m. I bring f over m to the left hand side and write this equation as x double dot plus omega 0 square x minus f over m is equal to 0, which can be written as x double dot plus omega 0 square x minus f over m omega 0 square is equal to 0. Redefine y is equal to x minus f over m omega 0 square, or equivalently as x minus f over k, and your equation looks like y double dot plus omega naught square y is equal to 0, and I know the solution for this in general is y is equal to c cosine of omega 0 t plus d sine of omega 0 t, and therefore, x is going to be equal to f over k plus c cosine of omega 0 t plus d sine of omega 0 t, where c and d are determined by the initial conditions. So, all that is happening is x has a constant shift and then it is oscillating about that point. More interesting case, however, is when we subject the oscillator to a force which depends on time. In general, a time dependent periodic force can always be written as a Fourier series like f n cosine of n omega t, where omega is the frequency of oscillation, and therefore, it is best that we analyze an oscillator subjected to one of these components, to a force f cosine of omega t, where omega is the frequency of the force. So, I am subjecting the oscillator to a force which varies like this with time. If I know the response of the system to f cosine omega t in general for any periodic force, I can find the response by superposing the solutions for each of these omega. In fact, I will assign you a problem later for two such forces being applied. For the time being, we focus on one frequency force being applied to the system, and therefore, the system I am looking at is a spring, mass at the end of it, and it is being subjected to a force f cosine of omega t. The equation of motion of this system is going to be mx double dot plus kx is equal to f cosine of omega t. If it is a damped oscillator, then the equation is going to be mx double dot plus b x dot plus kx is equal to f cosine of omega t. This is a free oscillator and this is a damped oscillator. And we want to look at the solutions of these two equations and see how they vary when omega is changed from one frequency to another in relation with the frequency of the oscillator itself, which is omega 0 is equal to square root of k over m. Let me first discuss the case of a free oscillator, because this will bring out the phenomena of resonance. So, for a free oscillator, the equation is mx double dot plus kx is equal to f cosine of omega t, which I can rewrite as by dividing by m, plus omega 0 square x is equal to f over m cosine of omega t. This is an equation which has a homogeneous part and a driving term. So, the general solution of this equation is going to be x t is equal to x homogeneous plus x particular. I need the homogeneous part to satisfy the initial conditions, because it is only the homogeneous solution that has freely fixable coefficients. So, this I can write as c cosine of omega 0 t plus d sine of omega 0 t plus x particular. The particular part of the solution depends on the driving term, and we want to find that. You see, this homogeneous part has two constants c and d, which will depend on the initial conditions. So, we find that for a free forced oscillator, for which the equation of motion is x double dot is equal to omega naught square x is equal to f over m cosine of omega t. The solution is x t is equal to c cosine omega 0 t plus d sine omega 0 t plus x particular. Now, it is very easy to see from these equations that x particular is going to be of the form some constant a cosine of omega t, because x if substituted here gives me cosine omega t, and second derivative with respect to time is also cosine omega t. When I substitute this here, I find that I have a cosine of omega t multiplied by minus omega square plus omega naught square a cosine of omega t is equal to f over m cosine of omega t. And therefore, since this equation is satisfied at all times, I get a is equal to f divided by m omega 0 square minus omega square. So, you see, for the particular solution there is nothing arbitrary, all the quantities are fixed, and therefore, the particular solution x particular is equal to f divided by m omega 0 square minus omega square cosine of omega t, and the complete solution of this equation x double dot plus omega 0 square x is equal to f over m cosine of omega t is x t is equal to c cosine of omega 0 t plus d sine of omega 0 t plus f over m cosine of omega t. I have given you the full solution of a free oscillator subjected to an oscillating force. Coefficients c and d obviously depend on the initial conditions. Let us now take an oscillator on which I start applying this force such that initially it is at 0 position at its equilibrium point, and it also starts with 0 velocity. X dot is also 0, and I want to determine coefficients c and d accordingly. When I substitute x 0 equals 0, I get 0 is equal to c plus f over, this is omega 0 square minus omega square, f over m omega 0 square minus omega square, or c is equal to minus f over m omega 0 square minus omega square. Similarly, when I take its derivative x dot, it will give me minus omega c sine omega 0 t plus omega d cosine of omega 0 t plus f over m omega 0 square minus omega square times omega sine omega t with a minus sign here. And since I know x dot at 0 is 0, it gives me d is equal to 0. And therefore, if I take an oscillator subject to it to a force f t equals f cosine of omega t and its natural frequency is omega 0, then the general solution starting with 0 velocity from the equilibrium point is going to be c, which was minus f over m omega 0 square minus omega square cosine of omega 0 t plus f over m omega 0 square minus omega square times cosine of omega t. This is the general solution. Let me write it clearly on the next page. So, general solution for a freely oscillating particle with natural frequency omega 0 subjected to a time varying force, which is f cosine of omega t, is x t is equal to, let me take this out, m omega 0 square minus omega square cosine of omega t minus cosine of omega 0 t. This is the general solution. This is under the condition that x 0 at time 0 and velocity at time equal to 0 are 0. How does this solution look? It has two frequency components, omega t and omega naught t. So, it is obviously not harmonic, but it is a superposition of two different frequencies. If I were to make this on a phasor diagram, which gives me an analysis of this. So, I am looking at the solution x t is equal to f over m omega naught square minus omega square cosine of omega t minus cosine of omega 0 t. Suppose I would look at it at t equal to 0. At t equal to 0, the term f over m omega naught over omega square cosine omega t looks like this, and at the same time the other term, let me draw it with blue color, is in the opposite direction. This term is this one. After time t, this term goes to, this phasor moves by an angle omega t. Let us assume right now that omega 0 is larger than omega. In that case, so applied frequency is smaller than the natural frequency. This phasor will move slightly more, maybe it comes here by omega 0 t. So, to get the net displacement, I add it to this one, and let me show by red, the net displacement is going to be like this. After some more time, say t2, this fellow may come here. Let us say this is omega t2. This will move much more. So, this will come, say, let us say here. So, at that time, this net displacement would be somewhere here. Let me show it by red, it will be somewhere here. You see, not only has the amplitude changed, it has also moved. So, it oscillates obviously between these two extremes, but the amplitude keeps on changing. If I were to see this displacement and plot it on displacement versus time plot, it would look something like this. It starts, the amplitude goes up, comes down, starts again, goes up, comes down, goes up, comes down, and so on. So, the amplitude sort of changes with time. I have given you a general sort of behavior when these two frequencies are superimposed. What I would urge you to do is do an exercise, choose an omega 0, let us say some number 2, choose an omega equal to 1, choose another omega 1.5, choose another omega 1.7, and so on, and try to plot these. I would give you a general feature that as you approach closer and closer to 2, you would see that this amplitude thing goes really far out and then goes down. But I would really like that you solve, you know the answer, solve these problems for 3 different omegas and plot it and see how the amplitude varies. What would be a very interesting question to ask now is, what happens when omega equals omega 0? Recall that the solution is x t equals f over m omega 0 square minus omega square cosine of omega t minus cosine of omega 0 t. I cannot substitute omega equals omega 0 directly here, because when I divided I assumed omega and omega naught were not equal. So, I take the limit omega going to omega 0. So, let me take omega to be slightly smaller than omega naught and substitute it here. So, x t in this case would be f divided by m times 2 omega 0, because this delta is very small, times omega 0 minus omega 0 plus delta times cosine of omega 0 minus delta t minus cosine of omega 0 t. So, this comes out to be f over 2 m omega 0 delta times cosine of omega 0 t, cosine of delta t, and delta being very small, I will take that as 1, plus sine of omega 0 t times sine of delta t, which I will take as delta t, because delta is very small, minus cosine of omega 0 t. In fact, delta finally I am going to take the limit of going to 0. This cancels. So, this answer comes out to be, this delta will then cancels with this delta, f over 2 m omega 0 times t sine of omega 0 t. what do you observe? You observe that x increases with time linearly. If I were to plot this, it would look something like this. X t I am plotting as f t over 2 m omega 0 sine of omega 0 t. Remember, when I take delta equal to 0, this is an exact solution. So, it will look something like this. You see, this part goes up linearly. This is the phenomena of resonance. So, when omega, the applied frequency, is exactly equal to the natural frequency, the oscillations grow linearly with time, and finally, the amplitude becomes very, very large, and in fact, so large that the oscillator may break. I am doing this phenomena here for free oscillator, because later we will see when we put damping in, resonance does not mean that the amplitude becomes large and keeps becoming larger and larger, rather it shows the maximum amplitude. Having done free oscillator and shown you the phenomena of resonance, now let me go to forced but damped oscillator. In this case, the equation of motion of which you are by now experts is going to look like mx double dot plus bx dot plus kx is equal to f cosine of omega t. Dividing by m, I get x double dot plus b over m I have been writing as gamma x dot plus omega 0 square x equals f over m cosine of omega t. Again, as in the case of free oscillator, I would have the general solution as the sum of the homogeneous part solution and a particular solution. So, I am going to have x t as equal to x homogeneous plus x particular, where the particular solution belongs to what force I am applying, and the homogeneous solution has those two independent constants. In general, this therefore would be e raised to minus gamma over 2 t. This we have solved in the previous lecture. C cosine of omega 1 t, where omega 1 is slightly different from omega 0, plus d sine of omega 1 t. This is the homogeneous solution plus x particular t. So, let me rewrite the solution for a forced damped oscillator. We have x t is equal to e raised to minus gamma over 2 t, c cosine omega 0 t plus d sine of omega 0 t plus x particular. As t becomes large, you see that this term would go to 0, and therefore, in the limit of large t, I am going to have only x particular solution. This does not get damped out, and this is known as steady state. Solution, because by now its own part has died down, and the only solution is because the oscillator is being driven, and it achieves a steady state where, because of the force, it keeps on moving in a very, very steady manner, and therefore, this is known as steady state solution. For the time being, we will focus on this solution. So, the equation that we are solving is x double dot plus gamma x dot plus omega 0 square x is equal to f over m cosine of omega t, and I am looking for its particular solution, because in the limit of large time, that is the only solution. So, in other words, I am looking for steady state solution. I could try a solution like x equals some amplitude times cosine of omega t. However, you see that when I take its first derivative to put in this term, I get a sine omega t term. Therefore, in general I should look for a solution of this form, a cosine omega t plus sine omega t. So, you see right away that the solution is not in phase with the applied force, or its phase differs. Let us see now what the general solution is. So, let us put this in here, x dot then would give me minus omega a sine of omega t plus omega b cosine of omega t. When I substitute, an x double dot is equal to minus omega square a cosine omega t minus omega square b sine of omega t. When I substitute these three in this equation, I am going to get and collect cosine omega t and sine omega t terms together. I am going to get cosine omega t minus omega square a. From this term, I am going to get plus gamma omega b, and from the last term I am going to get plus a omega 0 square plus collect the sine omega t terms, and I am going to get minus omega square b minus omega gamma omega a plus omega 0 square b is equal to f over m cosine of omega t. Since on the right hand side there is no term of sine omega t, therefore, this term must be 0, and this term minus omega square a plus gamma omega b plus a omega naught square must equal f over m. So, we have minus omega square b, let us see, minus gamma omega a plus omega naught square b is equal to 0, and we have minus omega square a plus gamma omega b plus omega naught square a is equal to f over m. When you solve these two equations, and I leave it for you as an exercise, you are going to get a is equal to omega naught square minus omega square over omega naught square minus omega square plus gamma square omega square, and b is equal to gamma omega over omega naught square minus omega square plus gamma square omega square. And therefore, the solution, steady state solution, is going to be omega naught square minus omega square, or times f over m also, times f over m, f over m over omega naught square minus omega square plus gamma square omega square cosine of omega t plus gamma omega f over m over omega naught square minus omega square plus gamma square omega square sine of omega t. Look at these two terms. I will take square root of the denominator out and write the solution as x t is equal to f over m over square root of x omega naught square minus omega square plus gamma square omega square times omega naught square minus omega square over square root of this term cosine omega t. Let me write this once, omega naught square minus omega square plus gamma square omega square plus gamma omega over square root of omega naught square minus omega square plus gamma square omega square sine of omega t, and this can be written as some amplitude times cosine of omega t minus phi, where the amplitude of the motion is f over m divided by square root of omega naught square minus omega square plus gamma square omega square, and sin phi is gamma omega over square root of omega naught square minus omega square plus gamma square omega square, or the square here. Cosine phi is omega naught square minus omega square over square root of this whole quantity, and tangent phi is gamma omega divided by omega naught square minus omega square. Let me rewrite these things on the next page. So, when I solve for x double dot plus gamma x dot plus omega 0 square x equals f over m cosine of omega t, I get a solution x t, which is equal to amplitude times cosine of omega t minus phi, where amplitude is f divided by m over square root of omega 0 square minus omega square square plus gamma square omega square, and tangent phi is equal to gamma omega over omega 0 square minus omega square. Notice that the displacement of the harmonic oscillator is now lagging behind the applied force. It is omega t minus phi. So, it responds slightly later. The amplitude depends on the frequency and obviously the force, how much force you are applying, and how much is lags behind depends only on the frequency and how much damping is there. More the damping, more the lagging behind, which is sensible from physical point of view. So, if I look at the phasor diagram at time t equal to 0, if this is the force, the displacement, obviously the magnitude is going to be slightly different, but if I just look at the phase relationship, is going to lag behind by this angle phi. If we translate this into the graph for displacement versus time, the applied force is of the form cosine omega t, f t is of the form f cosine of omega t, whereas x t is of the form some amplitude cosine of omega t minus phi. That is going to be slightly behind. So, it catches up with this displacement slightly later. So, this displacement is going to look something like this. This is x t, where this amplitude is f over m 1 over square root of omega naught square minus omega square plus gamma square omega square, and this phase angle is given by tangent phi equals gamma omega over omega naught square minus omega square. Notice that the steady state solution does not depend on the initial conditions. The initial conditions, whatever they did to the motion, have died out. Compare this with the situation that we solved earlier. For an undamped oscillator, the initial conditions affected the motion all the way, but here they die out because of the damping term, and the steady state solution only depends only on the applied force. The solution has a nice geometric interpretation in terms of phasors. Let us see at time t equal to 0, I am applying a force which is in horizontal direction. The net displacement is behind this by an angle phi. This is net displacement in this direction. So, this gives you a force which is omega square a. The velocity is in this direction. So, this is term which is x double dot. The velocity is this direction, which is gamma omega a. This is proportional to x dot. and the spring's own force is in the direction opposite to the displacement. Displacement is in this direction, which is omega naught square a. This is a term omega naught square x. So, you see, and this should end up at the tip of the force F. The net force is balanced all the time. The amplitude A and the phase angle phi should be such that this vector diagram closes on itself. The net motion now is that this entire assembly rotates counterclockwise with an angular frequency omega. That is the geometric way or phasor way or vectorial way of looking at damped harmonic oscillatory motion. As far as getting the solution of damped harmonic oscillator, which is forced, is concerned, we are done now. We solve for x double dot plus gamma x dot plus omega naught square x equals f over m cosine omega t, and got a steady state solution. Let me write it as steady to emphasize state solution as a function of time. It looks like f over m divided by square root of omega naught square minus omega square plus gamma square omega square cosine of omega t minus phi. This is a complete solution. The motion, the displacement lags behind the applied force by a phase phi, and it has an amplitude that depends on the force and the applied frequency. What remains to be done now is to analyze different situations. Let us first take the case of light damping and see what happens in this case. Remember, this case is where gamma square is much less than 4 omega 0 square, or gamma is much less than 2 omega 0. So, the amplitude in this case is f over m divided by square root of omega naught square minus omega square plus gamma square omega square. When frequency goes to 0, the amplitude goes to f over m omega naught square equals f over k. That means, at 0 frequency I am applying just a constant force and the mass is displaced. When frequency becomes large, the amplitude of the motion goes as f over m divided by, this is square, omega square, or f over m omega square. I have neglected this term in comparison with omega square. So, it is clear that if I were to plot the amplitude of the motion with respect to the applied frequency of the force, it will have a value f over k at omega equal to 0, and it will decay as f over m omega square far away. In between, its behavior for light damping is something like this, where the maximum occurs at omega equal to omega 0. If I increase gamma, it will be something like this. If I increase gamma further, it will be something like this. If you increase gamma, the maximum shifts slightly to the left, slightly to a value lower than omega 0, but for all practical purposes you can say that it is peaking at omega 0, and then far away it decays like this. So, if the driving frequency, if the frequency of the force that I am applying is equal to omega 0, the amplitude of oscillation becomes maximum, and this is again a reflection of phenomena of resonance. Recall that when there was no damping at frequency, driving frequency equal to the natural frequency, the amplitude was growing with time, it was not stopping. Here it becomes maximum, and this is again a phenomenon of resonance. We will see later that at resonance the power dissipated by the system and therefore power given to the system is also maximum. What happens if I go to heavy damping? If you recollect the previous lecture, we recall that in heavy damping, without force, no applied force, the motion finally came to a stop like this. But in this case, no matter what the damping value is, the motion will always be there oscillatory, because x t solution in steady state is some amplitude cosine of omega t minus phi. However, when the damping is heavy, then if I were to plot the amplitude versus omega, it has no maximum, it starts with f over m and just decays. So, for low frequencies, the oscillator oscillates with large amplitude, always less than f over k, sorry, and then for larger frequencies the amplitude becomes less and less and less. This is sensible because for low frequencies force has enough time to act on the system and therefore displaces it. However, as the frequency of the applied force goes up, the system does not react, it does not have enough time to react to the applied force and therefore its amplitude is very small. So, in general, if I combine the two, light damping and heavy damping, if I were to plot the amplitude of oscillations with respect to frequency, the curve looks like this, this is light damping, and there is no maximum for heavy damping, the curve just goes like this. Nonetheless, the system does oscillate even in the case of heavy damping when subjected to an oscillating force. I can say that in this direction gamma is increasing. So, in light damping case, I do have a resonance at this point omega 0, which really reflects that the maximum, the amplitude becomes maximum at that point. How about the phase of the system? Recall that the system, when subjected to this force, lags behind the force by an angle tangent phi equals gamma omega over omega 0 minus omega 0 square minus omega square. So, for very low frequencies, if this is omega and I were to plot phi omega, for very low frequencies the phase is almost the same as the applied force. So, the system is moving with the applied force. Then at omega equal to omega 0, the phase lags behind, the system lags behind by minus pi by 2. At omega equal to omega 0, this becomes 0. So, tangent phi is infinity, and when the frequency becomes large, this is minus pi. The force and the displacement are out of phase by pi. So, when the force is maximum, the displacement is minimum. So, let us see how the displacement and force are in relation with each other at different frequencies. This is time x t. Let us say this is omega much less than omega 0. The force is like this, and in this case the displacement will also be following roughly the same graph. I have not shown the amplitude correctly, only the relative phases. On the other hand, If omega is much larger than omega 0, then if the force is like this, the displacement would be out of phase by pi. This is x t. Black one is f t. In between, therefore, the phase is somewhere in between, and so on. So, we have talked about the motion, steady state motion in the case of light damping and heavy damping, and seen how in light damping cases at omega equal to omega 0 the amplitude is maximum. How about power absorption? In the system. Since there is friction in the system, obviously when the oscillator is moving, it is losing power due to heat, and that power is supplied due to friction, and that power is supplied by the force being applied. Now, power loss due to friction is going to be the force minus B v times V, which is equal to minus B x dot square. Let us put that in. So, power loss as a function of time is going to be minus B, which is nothing but m gamma. Remember, gamma was defined as B over m times x dot square, which is f over m times omega with a minus sign, divided by square root of omega naught square minus omega square square plus gamma square omega square sine of omega t minus phi square. This is the velocity square. When I open the bracket up, I find that P is going to be equal to, and this is power dissipated, is going to be equal to, let us see what this comes out to be. This is going to be f square gamma omega square over m omega 0 square minus omega square square plus gamma square omega square sine square omega t minus phi. So, power really fluctuates. If I were to calculate how much power is lost, average power over one cycle, that means I integrate the power 0 to t and divide by t. So, on an average per second how much power is being lost, sine square omega t minus phi averaged over a cycle is always a half. Recall RMS value from AC circuits in your 12th. So, average power comes out to be f square gamma omega square over 2m omega naught square minus omega square square plus gamma square omega square. This is the average power loss in the system. Is it equal to the power supplied? It should be. Let us calculate that. Power supplied is going to be equal to the force applied times the velocity, and this is going to be equal to f cosine of omega t. Remember, force is changing with time. Let me write this f t. Velocity is minus omega f over m divided by omega naught square minus omega square square plus gamma square omega square 1/2 times sine of omega t minus phi, and this can be written as minus omega f square divided by m naught square minus omega square square plus gamma square omega square raised to 1/2. Open this up, you get cosine omega t, sine omega t, cosine phi minus cosine square omega t sine of phi. So, power being supplied is fluctuating, and when I calculate average power, that means I integrate it with time t and divide by t. This term is sine 2 omega t and it is going to give me 0. Cosine square omega t integrated over a cycle is going to give me 1/2, and this minus sign takes care of this minus sign, and therefore, average power supplied is going to come out to be F, let us see this on the previous page, F square omega over m, F square omega over m, omega naught square minus omega square plus gamma square omega square raised to 1/2 sine of phi. Sine of phi, you recall, is gamma omega divided by this quantity. Therefore, this comes out to be f square gamma omega square and 1/2 because of cosine square omega t being averaged divided by 2m omega naught square minus omega square plus gamma square omega square raised to 1/2, which is exactly the same as we obtained earlier by calculating the power being lost. So, power supplied is equal to power lost, as must be the case for the steady state motion to sustain itself. So, we find that P average supplied or lost is equal to f square gamma omega square over 2m omega naught square minus omega square plus gamma square omega square. Let us see how this power changes as I change the applied frequency. And again considering light damping, you will see that this looks something like this, where the maximum is obtained at omega equal to omega 0. So, you see when there is resonance, that means the amplitude is maximum, the power that I need to supply to sustain the motion or the heat that is generated in the system due to friction is also maximum. And at omega equals omega naught plus gamma over 2 and omega equals omega naught minus gamma over 2, the power becomes half of the peak power. So, suppose this is P maximum, at these two frequencies this becomes P maximum divided by 2. So, this width, the frequency width by is gamma. This is known as width, full width at half maximum. Let me recap. When I plot for light damping P average versus frequency, P max is at omega equal to omega 0 and the power absorbed or power supplied falls by half at frequencies omega naught minus gamma over 2 and omega naught plus gamma over 2. This is known as the width of power absorption curve. So, width of power curve is gamma, resonance frequency is omega 0. You see right away that the quality factor is also related to the resonance frequency and the full width at half maximum. This is another way of looking quality factor Q that we had introduced in the previous lecture. So far, we have looked at steady state solution, but recall that the general solution x t is e raised to minus gamma over 2 t c cosine of omega 0 t plus d, or sorry, omega 1 t because damped oscillator, sine of omega 1 t plus x steady state. So, this factor really makes the solution, homogeneous solution, go down for times greater than 2 over gamma. For times less than, say 1 over gamma, we are going to have significant contribution from this solution also. So, in general, for such times we are going to have two parts of the solution, one part which is the decaying part, the other part which is the steady state part, and the total solution is the sum of the two. Let me show it here. The total solution may look something like this. And then finally, it goes to the steady state solution. These are known as transients because they exist for a short time of the order of 1 over gamma. However, what you notice, the transients could give you a very haphazard motion. Take an oscillator, force it with a certain frequency, and you will see initially it is moving back and forth in no regular pattern, and those are the transients. After some time, these transients or the homogeneous part dies down, and what you see is the steady state solution. This is one thing that I thought I should mention. Finally, I would like to state that I could also apply more than one force on the system. Not only that, their frequencies could be different, phases could be different. When I say phases could be different, I mean when one force is maximum, other force need not be maximum at that time. So, what would be the motion in general? As I said in the beginning of the lecture, a general periodic force can be a sum of many different frequencies. So, let us say if I have applied two forces, sorry, this should be B, K, X, two forces F1 cosine of omega 1 t plus alpha 1, where alpha 1 is a phase, plus F2 cosine of omega 2 t plus beta. So, there are two different phases, alpha and beta, two different forces. What would be the general motion? Recall that this is a linear equation, and therefore, principle of superposition holds. If I were to look at only steady state solution, x is steady state, it would be solution corresponding to F1 plus solution corresponding to F2. This is because of the superposition. Principle that tells me that any linear equation, for any linear equation, the sum of the two solutions is also a solution. You can substitute it back and see, because the equation, when you substitute m x f1 double dot plus b x f1 dot plus k x f1 is equal to f1 cosine omega 1 t plus alpha 1 is satisfied, and for 2 f2 cosine omega 2t plus beta is satisfied. Therefore, the sum satisfies on the right hand side this being added. I would like you to solve this problem, particularly see the case when omega 1 is nearly equal to omega 2. See what the sum of these two solutions looks like. What you will observe is that in this case, when omega 1 is nearly equal to omega 2, and let us take alpha to be equal to beta to be 0, you will see that the solution would be of this form. So, the amplitude would be varying with time, and the frequency of oscillation would be roughly equal to omega 1 plus omega 2 over 2, and this frequency of change of amplitude will be omega 1 minus omega 2 over 2. I would like you to do this exercise yourself by adding the two solutions. So, this is like the phenomena of beats. So, let us conclude our lectures on harmonic oscillator. These are some basic ideas about harmonic oscillators. You can obviously, this is such a robust model that you can keep doing more and more and more. We have looked at freely oscillating system. We have also looked at damped oscillations in the regime of heavy, critical and light damping. We have also looked at forced oscillations, resonance and power absorption of a damped force oscillation. I have also indicated to you how to get solutions for more than one force with different frequencies. What I have not covered is how to do this using complex algebra and many other terminologies like response functions and things like those, but given these basics, I am sure you will be able to cover them on your own.